Hi, everybody. Welcome back to lesson 6 in our introductory physics class. We are going to wrap up chapter 2 today and get started in chapter 3. And this is the slide where we left off last time. This give it a try example, looking at a velocity time graph this time and figuring out what information it can tell us. So if we remember, yesterday was a big introduction to calculus. So not just derivatives like we had started doing last week, but also these things called integrals, which is just a fancy way to say taking the area under the curve. And remember, we have to be kind of careful when we're thinking about that phrase, under the curve, because it really refers to that space that's between our graph line, our curve, and the x-axis. So in this example here, when we're taking the area under the curve, we have one area that's negative below the x-axis. We have that one area that's positive above the x-axis. And in these cases, it is totally valid to have a negative area. And again, that just means our graph line is below the x-axis at that point. So we have a negative height, if that. I mean, it's weird to think about having a negative height, but that's the general idea about what's happening. So we went through this part of the example, finding the total displacement of the object over this whole time interval of 18 seconds. So remember, when we have a position time graph, we can get to a velocity time graph by taking the derivative, or the slope of the line at each point. But when we're starting with a velocity time graph, to get to the displacement, we take the area under the curve. So I had broken it down into 5 different sections, rectangles and triangles. And then we mentioned yesterday as well that we could just find the equation for the area of a trapezoid and use that instead to simplify the problem. So I did pull up that equation and add it into this PowerPoint. So it will be there when I post it on Canvas later today. But once we figure out all of those areas of those sections and we add them all together, keeping in mind that some are negative and some are positive, we ended up with a total area under the curve, or a total displacement, of 84 meters, positive. So from here, if we wanted to go find out about the acceleration, what would we do from the information that we have? How would we find the acceleration knowing what we know? Good, Kobe. Yeah. We would take the slope of each section of this graph, right? The slope of velocity gives us acceleration. But that's not the next question that I want to ask you about this example. The next question that I want to ask you is to describe in words what this object is doing. So think about the velocity, what the graph actually means about its motion. Think about how that relates to its position. Take a second and think through this. What do you think this object is actually doing? All right, Vincent, you said moving backwards and forwards, staying constant, then backwards again. Constant from the start. Colby, you say it's a constant velocity and then it speeds up, and a constant velocity and then it slows down. Interesting. Any other ideas? What do you think this object is doing? Slowing down, then speeding up. Where'd it go? Slowing down, then speeding up to a constant, and finally slowing down. Another idea, at first it's going backwards, then accelerates forward, then constant forward, then slows down until stopping. Another idea, it's moving at a constant velocity in a negative direction, then starts accelerating in a positive direction, then goes into a constant velocity, then slows down in a negative direction. Another idea, it's also moving backwards for 6 seconds, then starts moving forward again. Thank you, Colby, for mentioning that time frame in there. That's really helpful. Anytime you're asked to describe specifically what an object is doing, think about what reference points you can give. So like, we can see that in our velocity time graph, something is definitely happening for the first 4 seconds, and then something changes after 4 seconds. So try to work those times into your answer as well, just so we can all be clear about what portion of the graph you're referring to. All right, so I'm seeing a lot of really good guesses. Let's go through together what is happening to this object. Okay, so it's moving backwards or west or whatever your negative direction is at a constant 12 meters per second for 4 seconds. And then it slows down. And we know it's slowing down because our velocity is getting closer and closer to 0, right? It's going up on the graph, but it's going from a negative velocity to one with a smaller magnitude until it crosses the line at 6 seconds. And when it crosses that x-axis, that means its velocity at that moment, at 6 seconds, is momentarily 0. So at 6 seconds, this object is momentarily stopped. And then it speeds up forwards or east, whatever your positive direction is, until 9 seconds. And we know that because there's a positive slope in our graph. So our velocity is changing over that time. It's speeding up. And then it maintains a constant speed forward at 18 meters per second for 4 seconds. And then it slows down to a stop in 5 seconds. And we know that it's slowing down during that last section of the graph because our velocity is going from 18 meters per second down to 0 meters per second. So that means it's slowing down. So go ahead and check yourself, check your thinking, see if you got your answer correct. Do you guys have any questions about this idea, how to figure out what the object is doing from looking at the velocity time graph? If we wanted to find the displacement of the object at any particular moment, all we would do is find the area under the curve from the beginning until that particular moment, and that would tell us its displacement. Again, it wouldn't tell us its position, but it would tell us the displacement, the change in its position. Okay, I'm not seeing any questions at the moment. Madeline, can we find the position? Not really from a velocity time graph. We can find the displacement. So we would just, assume a starting point. And then from that arbitrary starting point, we could know the position, well, the change in position. But we wouldn't be able to know the actual position apart from that arbitrary starting point that we're just assigning. And yeah, Colby, you put in plus C. I'm assuming that refers to whenever you take the integral of something, if you've taken calculus before, and there aren't defined bounds to your integral, then you have to add this generic constant plus C at the end of your integration. And that's because, remember, whenever we take the derivative of a constant, it's 0, it disappears. But that doesn't mean the constant wasn't there in, like if we take the derivative of position to get velocity, and our position equation is like 6x plus 1, when we take the derivative of that to find velocity, we would just get a velocity of 6. And that 1 6x plus 1 would go away because the derivative of a constant is 0. But that doesn't mean that the constant wasn't there. It's just if we start at the velocity and try to get to the position, we don't know what that constant actually was. We just know that there was a constant. So that's why we add plus c at the end of our integration. For those of you who have taken calculus before, you would have seen that. If not, and that didn't make any sense to you, that's totally fine. We're not going to be doing integrals for this class really anyway. Question, at t equals 6 seconds, the acceleration is 0. No, the velocity is 0 because the value of our graph at 6 seconds, the y value is 0. But remember, acceleration is the slope of our velocity time graph, and the slope at 0 is still some positive number. We could calculate it if we wanted to, but I don't want to right now. But we could find what that slope is, and that would be equal to the acceleration. What would happen if you took the integral of an acceleration time graph? You would get the change in velocity. So remember, we can go down our stack of graphs from position to velocity to acceleration by taking the derivative. Derivative goes down. We go up the stack of graphs, so from acceleration to velocity to position by taking the integral. So the integral of acceleration is change in velocity. Integral of velocity is change in position. Right, and we do have to be kind of careful about that because the integral of acceleration time graph doesn't give us velocity, it gives us the change in velocity. Just like the integral under, well, the area under the curve for the velocity time graph doesn't give us position, it gives us change in position. That change in is really important to remember. Okay, any other questions about this particular example? Going once, going twice. All right, if you have any other questions, feel free to just type them in the chat whenever you would like to. This kind of wraps up our chapter 2. So I have a chapter review that I want you to spend a couple of minutes thinking through. We did the same thing for chapter 1. I showed you some questions that might appear, like conceptual questions that relates to the material that we just went through in chapter 2. So spend a couple of minutes thinking through these. Jot down your answer on a piece of scrap paper and make sure that you understand these concepts before we move on to chapter 3. So take just a second and answer these questions on your own. Had some time to think through all of these questions. Give me a done or a ready or a let's go or something in the chat. All right, I see a lot of people answering readies, done. So we'll go ahead and talk through some of these together. Done, I think. Very valid. Give me just one moment, please. Okay. So we are going to just talk through some of these answers. I didn't create an answer slide. So we'll just think through some of these and talk about them together. So number 1, can an object with a constant acceleration reverse its direction of travel? Explain. So what did you guys answer for question number 1? Is that possible? All right. I'm seeing some not without changing its acceleration, No question mark? It is if acceleration has an opposite direction to its velocity. Yeah, so let's think about some like real life scenarios of this happening. Okay, so um, let's say, for example, we throw a ball up into the air and it'll come back down again in our hands. That's just a nice visual of something changing its direction of travel, right? So if we throw the ball up, it'll travel up for a little while, and then it'll eventually start traveling back down. It's reversed its direction of travel. But the acceleration that is acting on, well, that's being experienced by the object is constant. It's that constant acceleration due to gravity pulling it back down. And the acceleration due to gravity doesn't change just because the ball is changing its direction. It's a constant 9.8 meters per second squared pulling it down. And it's because that gravity is pulling it back down that the ball is changing its direction to begin with. So as long as the acceleration has the opposite sign of its velocity, then absolutely it is possible for an object to reverse its direction while still having a constant acceleration. Okay, that's a little tricky one. Number two, is it possible for an object to be slowing down while its acceleration is increasing in magnitude? What do you guys think? I'm getting some yeses. Can you guys think of an example, like a real life example of where this would possibly be happening? Speeding up in a negative direction. The one I said, the ball before hitting its maximum altitude. Reversing in a car. Colby, like if I start the NASCAR race in the wrong direction like a doofus and then I go backwards, that's an interesting example. Yeah, so remember as well, acceleration doesn't just refer to a positive acceleration, speeding up. We also call it acceleration when we're slowing down or changing direction. Anytime our velocity is changing, we refer to that as acceleration. So let's imagine you're driving really fast in your car, and then the light in front of you turns red and you have to kind of slam on your brakes. In that case, once you've slammed on your brakes, they're acting as like a negative acceleration. So that will slow down your speed, but the harder you press on the brake pedal, the more the magnitude of the acceleration is going to increase. So even though it's a negative acceleration, it can still increase in magnitude and work to slow you down. Does that make sense? Yeah, okay, good. So let's look at 2B. Is it possible to be speeding up while its acceleration is decreasing? What do you guys think? Yeah, I'm seeing some yeses. Yeah, absolutely it is possible to be speeding up while your acceleration is decreasing. Gabriel, you say it depends on the points of reference. I would argue that most of these probably depend on your point of reference. That's a good point to bring up, Lowell. But yeah, let's see if we can think of a real life example. So let's say, again, you're driving in your car. I think that's probably like a pretty common thing to visualize. So you're driving in your car, the light has turned green, so you push your foot on the gas pedal. That, of course, makes you speed up. And then after a while, once you reach the speed limit, because we all always drive the speed limit, you kind of release your foot from the gas pedal a little bit. And so that would decrease your acceleration, but you're still speeding up a little bit as you're decreasing your acceleration. And then, of course, once your foot comes off the gas pedal, you would, if there were no friction, you would keep going at a constant speed. So that might be a good real life example for that. Okay, number 3, under what conditions does the magnitude of average velocity equal the average speed? What do we think? When it is a straight line motion. Oh, when you only move in the positive direction, okay. Do you remember what the word magnitude means? Hopefully. Right, so magnitude means the size, the amount of our average velocity. And the only difference between velocity and speed is that velocity we're interested in the direction and speed we're not interested in the direction. So speed in itself is the magnitude of velocity, right? They both tell you how fast you're going. Velocity just adds in that extra direction piece. But if we're just concerned about the magnitude of velocity, that tells us how fast we're going. That is the speed. So under what conditions does the magnitude of average velocity equal the average speed? Always, because speed is the magnitude of velocity. Number 4, can you have a zero displacement and a non-zero average velocity? What do we think? Remember the equation that we used for average velocity? If you take notes, you might have it in your notes. If not, then this PowerPoint will be posted later today anyway. But remember, average velocity is the change in position over the change in time. Change in position is displacement. So if we have a zero displacement over any length of time, 0 divided by anything is 0. So no, we can't have a zero displacement and a non-zero average velocity because we use displacement to calculate average velocity. Bonus question, can we have a zero displacement and a non-zero instantaneous velocity? Yeah, absolutely we can. If we're just looking at the velocity at any particular point in its traveling, in its path, we could have all kinds of different velocities, instantaneous velocities, but still end up at the same place where we started. That is absolutely possible. Okay, number 5, can you have zero velocity and non-zero average acceleration? I'm seeing some no's. So this one is kind of tricky because it just says velocity. It doesn't say like a zero average velocity or a zero change in velocity. It just says a zero velocity. And so when we see just the word velocity, remember we have to assume that's talking about instantaneous velocity. We will always specify average, but we're just going to assume instantaneous. So if we're assuming an instantaneous velocity, then yes, we absolutely can have zero instantaneous velocity and a non-zero average acceleration. And that would be, again, the case of throwing a ball up in the air and it coming back down. That moment that the ball is changing direction, Its velocity is going from positive to negative. Right at the very top there, its instantaneous velocity is 0. But the acceleration hasn't changed. It's still a constant 9.8 meters per second squared downward. So we'd have a constant average acceleration that's a number, negative 9.8 meters per second squared, and we'd have a 0 velocity. So absolutely that can happen. Number 6, a car is traveling west. Can it have a velocity toward the west and at the same time have an acceleration toward the east? Under what circumstances? So what do you guys think? Is this possible? Colby, it's definitely possible. Yes, absolutely. It is for sure definitely possible. Thank you, those of you who are responding in the chat. Yeah, we can absolutely have that. Right, so if we're traveling west and we have an acceleration toward the east, what would be happening here, or under what circumstances? That would be slowing down to the west. Or if we think about like west as being backwards, that would be slowing down as we go backwards before we go forwards again. Hitting the brakes, yeah, absolutely. We're traveling west, but we're hitting the brakes. That would be an acceleration toward the east. Great example. Air resistance, potentially, yeah, potentially air resistance. If we have a big enough, well, yeah, air resistance, that's a good example. Okay. And then last question, number 7, a truck is at an initial position, x1, of 277 meters at time 1 of 16 seconds. And then at the second position, 19 meters at second time, 25 seconds. Sketch 2 different possible position time graphs for the motion of this truck. So like I said, I didn't actually type an answer slide for this, so I haven't sketched out 2 different possible position time graphs, but there could be a bunch of potential answers to part A, as long as at your first time of 16 seconds, your position is 277, and at your second time of 25 seconds, you're at a position of 19. Anything could happen in between those 2 points. It could be a straight line, it could be a curve down, it could be like a smiley face. Anything could happen between those points, and they would be valid position time graphs. Part B, is the average velocity between these 2 points the same on both graphs? Why or why not? Aren't there technically like infinite potential graphs? Yes, there are infinite potential graphs for that, for part A. So for part B, yes, they would be the same. Remember, average velocity is displacement or change in x over a change in time. Regardless of what pathway you drew between those 2 points on your graph, you're still starting at 277 and ending at 19 meters. And so our displacement is the difference between those 2. So no matter what shape graph you made for part A, your average velocity will be the same. Is the instantaneous velocity between those 2 points the same on both graphs? No, it wouldn't be. That would depend on the shape of your graph, because remember, instantaneous velocity is the slope of the line at each point. So if you had a diagonal line connecting those 2 points, then your instantaneous velocity would be the slope of that diagonal line. If you had a curve connecting those, well, I can't make my arms do that, but whatever. If you had a curve connecting those 2 points, then the instantaneous velocity is the slope of each part of that curve. And that would depend, again, on the shape of your curve. So while we can have the same average velocity, we will not have the same instantaneous velocity. Okay, so that wraps up our chapter review. I didn't put in any review questions about derivatives and integrals. We did some practice with those yesterday, of all things. I'll try to throw some in into our chapter 3 PowerPoint. But these are questions that I took from the back of the book, and they just didn't have any questions about derivatives and integrals. So I'll brainstorm some of those, throw them at you maybe tomorrow. But on a scale of 1 to 5, how do you feel about these topics of position, displacement, velocity, acceleration? Okay, looks like we're feeling pretty good. Wow, Vincent, very specific, 4.93. I like it. Okay, so that's great news. Do you guys have any questions before we move on into chapter 3? All good? Okay. Well, give me a moment to pull up um, the next chapter 3 PowerPoint. Um, chapter 3, Colby, is about motion in 1, 2, and 3 dimensions. Is this PDF on the Canvas files though? Not yet, because we hadn't finished going through it. But I'll add in an answers slide to our chapter review questions that we just talked through. And then I'll post the PDF on Canvas later today. Okay, so let's share our chapter 3 PowerPoint. Okay, can we all see chapter 3, motion in 1, 2, or 3 dimensions? Yes, good. It bothers me a little bit that there's a typo in our meme, but not enough to not put it in. So there you go. Okay. All right. So the reason this is called chapter 2 and 3 is because we're doing the last 2 sections of chapter 2. I just feel like it flows nicely with this material as well. We're taking motion with a constant acceleration in one direction. So either like dropping a ball and it falling straight down, even throwing a ball up and it falling straight back down. And then we're going to expand that into 2 dimensions. So like throwing a ball forward. So that's why it's called, chapters 2 and 3. We're going to add in those last couple of sections. Okay, so I will say that this chapter is pretty equation heavy. So I would recommend that as we derive some of these equations, that you write them down like on a Post-it note or an index card or something in your notes, just so you can have them handy to look at as we do some of these example problems together. So we're going to be deriving with derivatives to start off. Okay, so we're going to start here with this function, this position function, x equals beta t plus 1/2 gamma t squared. So that B looking symbol is the Greek letter beta, and the weird Y looking symbol is the Greek letter gamma. And those are just random variables that we're using as placeholders. So we'll replace them in just a moment. Okay, so we want to take the first derivative of this function with respect to time to get velocity. So think about the derivative rules that we talked about yesterday, the power rule and the sum rule. See if you can come up with the first derivative of this function with respect to time. So since we're doing the derivative with respect to time, remember any variable that's not a t, we're going to treat as a constant. Okay. So take a quick second, think about this first derivative. Okay, so our first derivative, I see an answer there in the chat. Great job. Our first derivative, so again, this notation here, dx over dt, is our notation for taking the derivative with respect to time. So the derivative of x with respect to time is velocity, and that would be beta plus gamma t. So remember, we're going to apply the power rule here, and the exponent on beta t, the exponent of t is 1. So when we multiply the coefficient by the exponent 1, we get beta, and then we subtract 1 from the exponent. So 1 minus 1 is 0. Anything to the 0th power is 1. So we get the derivative of beta t is just beta. And for the second chunk there, we multiply the coefficient by the exponent. So 1/2 times 2 is 1. Gamma stays constant. And then we subtract 1 from the exponent. So we get gamma times t. Okay. So that's our first derivative. Now take the second derivative. So you're going to take the derivative of the derivative. What will that become? Apply your power rule. Only gamma. All right. Good. Absolutely. So the derivative of velocity with respect to time gives us our acceleration. Beta, remember, we're going to treat it as a constant, so that would disappear. The derivative of a constant is 0. So we're left with just gamma as our derivative of this function. Well, if we know the acceleration equals gamma, then anytime we see gamma in our equations, we can replace that with an a for acceleration. So I plug that into that second line there, the first derivative, dx dt equals velocity. So that equation becomes velocity equals beta plus at instead of beta plus gamma t, right? So if we think about this, if we know that acceleration is the change in velocity over the change in time, then that at in that equation is our change in velocity. Right, we can take that a equals delta v over delta t, kind of rearrange that to get a times t, so that v that we see in that equation, v equals beta plus at, that v is really the final velocity, and beta is our initial velocity. So anywhere we see beta then in our equations, we can replace beta with initial velocity. And so that first equation then becomes x equals initial velocity times time plus 1/2 acceleration times time squared. And that second equation for velocity becomes final velocity equals initial velocity plus acceleration times time. So these two equations are pretty important equations. They're part of what we call the kinematic equations. And so these are two really helpful equations of motion that we'll be using a lot in this next chapter. Okay, so physics is more than just a bunch of equations. You know, we don't just want to teach you guys how to plug and chug, plug numbers into an equation and get an answer, because part of the fun of physics is like creating equations that are specific to a unique problem. So you got to remember too, like all of these equations that we use in physics were created by somebody, most likely Isaac Newton, because what did he not do, right? He like invented calculus to explain physics. Who does that? I just, but anyway, that's what he did. So all of these equations that we'll be using were created to solve specific types of problems. And so when you take physics in college, especially on if you go on to like a grad school level, like I know some of you want to do, you'll have to create your own equations to explain the problems that you come up with. So it's more than just plugging and chugging into equations, which is why I wanted to show you how we can derive some of these from the other ones. But there I have a big list of kinematic equations for you. I don't want to spend time deriving all of them. It's in the textbook if you want to see it, but we just don't have time to go through and do all of them. So these are what we call the kinematic equations. Kinematic means of motion. So these are all of our equations that describe the motion of objects. And these are all for constant acceleration. That's a really important thing to note. All of this chapter is just thinking about constant acceleration. So we see there at the top the two equations that we should already be familiar with. Average velocity is change in position over change in time. Average acceleration is change in velocity over change in time. And then you can see kind of nestled in there, we have two of the equations that we just derived on the previous slide, the VF and that second delta X equation. We derived those just a moment ago. If we look at that top delta X equation, delta X equals 1/2 VI plus VF times time. Well, 1/2 VI plus VF is really just our average velocity. Right, when you take an average of something, just like in your math class, you add them all up and divide them by how many there are. So if we're taking the average of two velocities, we add them together and divide by 2. So really, that equation, that delta X equals 1/2 VI plus VF times time, is just that top equation rearranged. And then plugging in what we know average velocity is when we take an average. That bottom equation there, VF squared equals VI squared plus 2A delta X. You can derive that equation from some of these other ones, but again, I'm not going to go through that for the sake of time. So these equations, these kinematic equations, I wrote them all in terms of X, but they also work in the Y direction. So if we're not thinking about motion horizontally, but we're thinking about like dropping a ball, we would just replace X with Y. So our delta Y would be our change in height. And we would use, our acceleration in the Y direction or a velocity in the Y direction. So these equations are equally valid in both cases, but we do not mix the two directions together, right? We can't say delta X equals a Y velocity times time. Like that, you can't do that. They apply to both X and Y directions, but you have to keep them separate. So if you're thinking about a Y direction, everything in that equation has to be in terms of Y. And if you're thinking in an X direction, everything in the equation has to be in terms of X quantities. Okay. Different textbooks and different professors will write these variables slightly differently. So you might see initial velocity written as VI, I for initial, or V0, which is pronounced V naught. And that's just saying like at time equals 0. That's your velocity. So your initial velocity can be written both ways. Your final velocity or your current velocity could be written as either VF or just V, because that, again, we're assuming velocity pertains to instantaneous velocity, and we just call that velocity. So VF or just V means your final or your your current velocity at whatever moment you are being asked to find. Okay, so here's an example. We have an accelerating car. So a car starts from rest and accelerates at a constant rate of 5 meters per second squared. What is the velocity of the car after it has traveled 30 meters? How much time has elapsed? And calculate the average velocity. Okay. So remember, when we're dealing with an acceleration, that just tells us how the velocity is changing with time. So an acceleration of 5 meters per second squared means that every second our velocity is increasing by 5 meters per second. So if we start out from rest, after 1 second, our velocity has increased by 5 meters per second. So our velocity then is 5 meters per second. At 2 seconds, we've increased our velocity another 5 meters per second, and so on. So what I want you to do first is to choose which equation to use for each part of the question. I'll give you a second to think through them. I have them down there in that orange box. Which equation would be best to use to solve each of these different problems? Okay, so let's think through these equations together, right? So for part A, sorry, that's a lot to look at once, but we'll go through it. For part A, we need to find the final velocity, right? What is the velocity of the car after it's traveled that particular distance? So we want to find an equation that contains the variable for final velocity. So we can see VF appears in equation 3, in equation 4, and in equation 6. Okay. So now let's think about the things that we are given in the problem. Okay, we're given the change in position. It's displacement of 30 meters. So we can see change in position in equation 1, in equation 4, in equation 5, and in equation 6. So we could use one of those, but let's look at the other things that we're given. We know the car starts from rest, so its initial velocity is 0. Anytime you see from rest, your initial velocity is 0. Okay, and we see initial velocity show up in equations 3, 4, 5, and 6. So any of those could be helpful. We're also given the acceleration of 5 meters per second squared. And acceleration appears in equation 2, 3, 5, and 6. So looking at those, we want an equation that contains all of those if possible. If we can find just one equation to use instead of having to do multiple, obviously that's ideal. In physics, we kind of want to be lazy as much as possible. So if we can only do it, if we can do it in just one step, as opposed to like 3, let's do it in one step. So looking at these equations, the only equation that contains all of the variables, both the one that we're looking for and the ones that we have, is equation 6. So we're going to use that one. Okay. And we're looking for the final velocity. So we're going to take the square root of initial velocity squared plus 2a delta x. Remember, our initial velocity was 0, our acceleration was 5, and our change in position was 30. So once we plug all of those numbers into that equation, we get our answer of 17.3 meters per second. Okay. Next question. How much time has elapsed? Again, we could use any equation that has time in it. And really, all of them involve time except number 6. The first two just have a change in time. But if we assume that we're starting from an initial time of 0, we could also use equations 1 or 2. But we also see time by itself in equation 3, 4, or 5. So pick whichever one is the simplest, right? We have all of those other pieces to it. We have delta x, vi, vf, a. We have all of the things that we need. So again, be lazy, choose the simplest one. And in this case, that's equation 3. So our final velocity is initial velocity plus acceleration times time. Rearrange that equation to get time, and we find that it's a time of 3.46 seconds when the car has reached 30 meters. All right, calculate the average velocity. Well, there's really only one choice in this case, right? There's only one equation that contains average velocity as such. Equation 4, remember I had said 1/2 VI plus VF is technically the same thing as average velocity, but clearly number 1 seems the very simple choice. So average velocity is our change in position, 30 meters, over our change in time, 3.46 seconds, and that gives us an average velocity of 8.67 meters per second. All right, any questions about this example? Good, I'm seeing some all goods. Nope, no questions. Okay, great. All right. That gift just makes me laugh so much. I love it. But anyway, skydiving cats. Have any of you ever gone skydiving? My husband took me, oh gosh, 2 years ago. My son was born at that point. It was so cool. I was teaching physics at Melbourne High School at that time. And so, of course, like when you go skydiving, you can order a video of your trip with like a GoPro or something. And so I got the video, and like the whole time in the video, I'm just talking about the physics of skydiving because I'm a nerd. But yeah, it was super, super cool. I definitely recommend it. From like a reputable source, of course. Don't just jump out of a plane on your own. But yeah, it was really interesting. Anywho, the most familiar example of motion with a nearly constant acceleration is an object falling down due to Earth's gravity. So like anytime your pencil rolls off your desk, or you drop your phone and your heart like stops for a moment, or you jump out of an airplane, because why not? That's an example of what's called free fall motion. So in the 4th century BC, Aristotle thought that heavy bodies fall faster than light bodies proportionately to their weight. That is incorrect, but it's actually one of the most common misconceptions that still exists, still stumps students today. Probably if you went to some random person on the street and you ask them questions about physics, because who doesn't do that in their free time? And you ask them, like, between an apple and a hammer, which one would hit the ground first if you drop them? Most people would say that the heavier one will hit the ground first, and it falls faster because it's heavier. And really, that's not true. It took like 1900 years after Aristotle proposed this, that Galileo argued that objects should fall with a constant downward acceleration independent of their weight if we can ignore the effects of air resistance. So of course, air resistance acts on objects depending on their shape, not their weight necessarily, but their shape affects how much air resistance they feel as they fall. So if you can do this, if you can remove air from the scenario and drop things with different weights, they will fall at the same rate. They will hit the ground at the same time. And NASA astronauts did this experiment on the moon with a feather and a hammer, and they hit the ground at the same time because we removed, well, I guess we didn't remove air, but there isn't air resistance up on the moon. And so, yeah, they kind of proved that um, that the mass doesn't affect how bodies fall. And of course, like if you remember kinematic equations from just a moment ago, mass does not appear anywhere in any of them. So the mass doesn't affect our motion in this sense. Mass affects other kinds of motion, but not free fall acceleration. Yeah, it is super cool. They've also repeated the experiment on Earth in like these huge vacuum chambers where they can just suck all the air out of the room and drop things. And the same result happened. They dropped like a bowling ball in a feather, I think, in one video that I saw, and they fell at the same rate. So if you can remove air resistance, um, you get the same result that Galileo proposed. So that's super cool. I think that's awesome. But we have what's called free fall whenever we're falling or rising with no outside forces acting on it except gravity. Gravity is the only force that's acting on the object because, again, we're ignoring air resistance. So with air resistance, weight still doesn't matter, right? Only the object shape. I'm pretty certain that it's the object shape that affects air resistance. Of course, this scenario, this idea of free fall is idealized because, you know, on a day-to-day basis, we can't just like suck all the air out of the world to do an experiment. So this is definitely not realistic as such. So once again, we're going to be looking at the ideal case for physics 1, but free fall is when we're falling or rising, so like throwing a ball up in the air with only force acting on it being gravity. There goes the cat. Okay, anywho. So acceleration due to gravity. This gets a special symbol because it's such an important number, and we'll be using this just so much in the next couple of weeks. So we give it the symbol lowercase g, but it stands for an acceleration due to gravity. It's not the force of gravity, it's an acceleration due to gravity. That's another thing that students tend to get mixed up. This is not the force of gravity. This is the acceleration due to gravity. So gravity making things accelerate. That value is 9.8 meters per second squared. That's an approximate value near the surface of the Earth. And it does vary slightly with your location on Earth. So like if you're at sea level versus way up on a mountain, that value is a little bit different. I think here in Melbourne, like the Coast Guard did an official test of the acceleration due to gravity, and they found it to be 9.792 meters per second squared here in Melbourne, Florida. But if we take an average of all of the locations on Earth, we approximate it to be 9.8. Okay, so on the moon, just to give you a little bit of perspective, the acceleration due to gravity is 1.6 meters per second squared. So that's why you see all those videos of like astronauts bouncing along the moon and they look like they're moving really, really slow because gravity isn't pulling them down as hard. Near the sun, the acceleration due to gravity would be 270 meters per second squared. That's nuts. Yeah, so the location on Earth affects the acceleration due to gravity, and your location in the solar system or in the universe affects it as well. But G is the magnitude of a vector quantity. And since it's a magnitude, it's always positive. Right? It's like the absolute value is always positive. So an object that's accelerating due to gravity will accelerate at negative 9.8 meters per second squared in the y direction. Or that's just another way to say 9.8 meters per second squared down. So we can throw a ball upwards and it would travel upwards, but it's still accelerating downwards. Just like we saw in our chapter review from chapter 2 at the beginning of this class. We can definitely have an object moving upward, but have a downward acceleration. That happens anytime you throw something up in the air. You can play basketball there. Yeah, I am terrible at jumping. Like my husband makes fun of me all the time for it because he's a skateboarder and like used to do parkour and all of that stuff. Um, and so he just thinks it's so funny that my like maximum jump is about this far off the ground. Like I just can't jump. Um, so maybe I could play basketball there. Does he do parks? He hasn't done parkour in a long time. He is from California, so he used to do parkour in like San Jose and San Francisco and big cities and stuff there. As far as skateboarding goes, he, yeah, skateboarding. He does go to skate parks. Not really a whole lot since we've had kids. They take a lot of time. Um, but yeah, he likes to do like street skating and stuff like that. Again, in San Francisco and San Jose and stuff. Um, but also here in Florida. It's just so hot in Florida. It's miserable. But yeah, anyway, sorry, off topic. Okay, so here's another example of an object in free fall. A coin is dropped from the Leaning Tower of Pisa. It starts from rest and falls freely. What is its position and velocity after 1 second, 2 seconds, and 3 seconds? So here we have our diagram from the textbook. So let's think about this. Okay. Here I just went ahead and derived the equations. Well, not derived, but manipulated the equations that we're going to be using. So we're starting out with our kinematic equation in the y direction. This is one that well, it's a version of one that we saw on that other slide. So previously we had seen it to be delta x equals v0t plus 1/2 at squared. But remember what that delta x means. It means the change in the object's x position. So that would be x final minus x initial, right? So on our equation here, where we have the y equals, this is like our y final equals, and instead of having y final minus y initial, we just brought the y initial over to the other side of the equals. So y final equals y initial plus our initial y velocity v0y times time plus 1/2 a, and that's again in the y direction, times time squared. So just for the sake of simplicity, I am not going to put my 0 point at the ground. I'm going to put my 0 point where I am dropping the coin. So the reason I'm doing that, and you can pick, wherever you want to be the 0 point, as long as you keep it consistent throughout the whole problem. But the reason I'm choosing it to be at the top there is just so I can cross out that initial y position and not have to worry about it, right? We don't have to know how tall the Leaning Tower of Pisa is right off the get-go. We can set the top to be our 0 point, and we're good to go. That takes it out of the equation. We're dropping it from rest, so our initial y velocity is 0, so that goes away in our equation. And we know that our acceleration in the y direction is our acceleration due to gravity, and that is a downward acceleration. So our equation becomes y equals 0 plus 0 plus 1/2 negative g t squared. Again, negative g because it's pulling it downward. We know g is approximately 9.8. So when we plug that number in there, 1/2 of negative 9.8 is negative 4.9 meters per second squared times time squared. So at this point, this equation that I have created is valid at any time in our problem. And because the question asks you for the position and velocity at 3 different times, So I can just plug each time into that equation now that it's simplified and ready to go. We can do the same basic idea for our y velocity as well. And again, this is an equation that we saw in our kinematic equation slide. Our final y velocity equals our initial y velocity plus our y acceleration times time. But again, our initial y velocity is 0 because it's starting from rest. And our acceleration in the y direction is gravity pulling it down. So that would be a negative 9.8 meters per second squared times time. That gives us velocity. So when we actually plug our time values into these equations, we can see that our y position, or like our height downward from our starting point, the distance that it's fallen downward, I guess, is a better way to say that. At 1 second, that distance is negative 4.9 meters. So, of course, remember that negative means it's below the starting point. It's fallen down as opposed to falling up. And that y velocity at that instant is negative 9.8 meters per second. Again, negative because it's traveling downward. So at 2 seconds, we plug 2 in for t, and we get a y position of negative 19.6 meters and a y velocity of negative 19.6 meters per second. And then if we plug in 3 for our time, we get a position of negative 44.1 meters and a velocity of negative 29.4 meters per second. Okay, cool. Do you guys have any questions about our kinematic equations so far? Okay. So I don't have them posted yet, but once class is done, I will have some free fall practice problems for you to do. I'll post them on Canvas, and we're gonna pick up here tomorrow. We're gonna do one, maybe two more examples of this motion in one direction before we expand it into 2 dimensions. So not just dropping things, but throwing things, what effect that has on our object. So we'll pick up with that tomorrow. And if you guys have any questions, comments, concerns about the lesson today or previous lessons or anything like that, feel free to hang out after I stop the recording and ask away. But if not, I hope you have a great day and I will see you guys tomorrow.